Okay, so I'll do 14 and 15 together. They're both hypothesis tests where we have to pretty much run through the entire hypothesis testing process. So I'm going to draw your attention back to a formula sheet here. Chapter 8 is the hypothesis testing chapter. We'll be using these first two formulas here, the z-test formula and the t-test formula. And just like the problems before, how we know we're using a z-test versus a t-test, same procedure, same reasons why. If we know the population standard deviation, using a z-test. Also for a z-test, if the number of data points, the number of values is less than 30, you must have a normally distributed population. So we say n should be greater than or equal to 30, as I said before. For the t-test, this is if we don't know the population standard deviation. We know the sample standard deviation, and the degrees of freedom here would be n minus 1. Something else to draw your attention to, further down on this formula sheet, there's two methods that we cover to do hypothesis testing, and the procedures are actually on this formula sheet as well. The procedure for the traditional method, 5 steps here, and the procedure for the p-value method, the 5 steps are here. I'll try to show both methods, and whichever method you find more appropriate, whichever method, in some cases the p method won't necessarily work, won't be able to be done, but if you can use it and you like it, use it. So I'll go back and forth between this and those formulas there. So a test is made of H sub 0, the null hypothesis. I'll write it here. The null hypothesis is the mean. The population mean is 55. The alternative hypothesis, H1, sometimes called HA, is the mean is the greater than 55. So this tells you this is a right-tailed test because we're talking about the mean being greater than 55. So this is a right-tailed test. If I was to draw something here, this is where we're concerned with. If we're using the first method, if we're using the traditional method, the critical region would be that region. The critical region would be this region here. The rejection region would be this region here. Okay, so we have that. The sample size n is 62. X bar, the sample mean is 62. Both are 62, interesting. And the population standard deviation is 27. And alpha is 100th, 0.001. We're talking about 99%. So we know the population standard deviation. Because we know the population standard deviation and n is greater than or equal to 30, this is going to be a z-test. Okay, and if it's a z-test, we know if we're using these formulas here, if I go back to chapter 8, we know we're using this first formula here to calculate the test statistic, right? To calculate the test value. Since this is a z-test, we know the population standard deviation, n is greater than or equal to 30, using this formula here, and I'm going to write that down. So I know to compute the value of the test statistic, that's what we're asked to do here. C is equal to x bar minus the mean over sigma divided by the square root of n. I know the students have a lot of problems with this here, so I'll show you how to do this calculation so you don't make any mistakes with this problem. Okay, so if I go back to our steps, so first we'll do the traditional method, right? The hypotheses the hypothesis was already stated. Sorry. The hypothesis was already stated. We're not exactly told what the claim is here. That's okay. For the word problems that you may see, you should be able to identify what the claim is. Right? So we've got the first step down. Find the critical values from the appropriate table in Appendix C. So let's find the critical values first. I was going to do it in a different order, but let's find the critical values. So let's find, I'll draw a line here since I'm doing two different methods. Right, this is the traditional method. So the Z critical value. The Z critical value, let's find that. So that's based on this alpha level, right? That's where I'm trying to figure out what this rejection region is going to be here. That's based on this alpha level. See, this region here is going to be 0.01. Right? That region is going to be 0.01. That's our rejection region. So I need to find that Z value, that critical value that gives this region, this alpha, this critical region, this rejection region of 0.01. And I go to the table for that. I want to find the Z value that gives me 0.01. And if you memorize those values from earlier, that's even better. And again, sorry. This is symmetric, right? This is symmetric. So the table doesn't give me this value, but on the other side here, if I find 0.01 here, and I get this Z value, it'll be negative. I just change the sign to positive, and I'll have this one to the right. So that's not a problem for us. So we look for 0.01. 0.01, 0.01, 0.01. Where is it? 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 My eyes are bothering me, so I can't really see here. Here we go. Here we go. Here we go. Here we go. That looks about right. I'll say negative 2.33, right? For 0.01. This rounds up to 0.01, negative 2.33. So here, negative 2.33. And here, positive 2.33. That's my Z critical value, 2.33. That's step 2. That's the Z critical value. This is an important value here. That's this value. That's like our cutoff value. So we're going to calculate our Z test statistic. And if that test statistic is in this region, if it's greater than 2.33, if that value, this value that we calculate here, is in this region, is greater than 2.33, reject the null hypothesis. Okay, so let's calculate. Let's see. Probably should use a different color for that. So X bar, 62, minus the mean. What does that mean? 55. That's the one we're concerned with. Divided by the standard deviation. The population standard deviation is 27. Divided by the square root of n, the square root of 62. So let's do this piece by piece. First, let's find this numerator, right? 62 minus 55, that should be 7, all day, every day. And then I'm going to do this in the calculator. This denominator, I'm going to compute that in the calculator. So we've got 27 divided by the square root of 62. I'm just splitting it up like this because I see a lot of issues happen with this. So let's use 4 decimal places, 4290. So 3.4290. I'm going to have to put the 0 there. So then the Z test value is going to be approximately, let's divide 7 divided by 3.429, 2.04. That is our test statistic. That's the value. That's what we just calculated here, this test statistic. So now again, I check this test statistic against my critical region and determine if I'm going to reject, if it's in that critical region, that rejection region. So 2.04 is not greater than 2.33. It's actually less. It'll be somewhere in here. So because it's not in this critical region, my conclusion, determine if 8 sub 0 is rejected. My conclusion is do not reject 8 sub 0. Do not reject 8 sub 0. There's not sufficient evidence to reject that null hypothesis. Okay? Or if this was the claim, there's not sufficient evidence to take that claim as true. Okay? This is this approach here. Let me go back to it. Compute the test value, make the decision to reject or not reject, and summarize the results. So those are our steps there. In this case, it's more difficult to summarize the results because we don't have a real life situation to go back to. All right, now the p-value method. The first step is the same. State the hypotheses and identify the claim. Compute the test value. Right? Those two processes are both the same. First step and third step here. First step and second step here. Okay? So let me go back. So here's the p-value method. P-value method. I should probably use a different color. Let's use blue. Blue and red, right? All right. The battle continues. Okay. So let's go back. The steps. State the hypothesis and identify the claim. That's done. Compute the test value. We did that here, right? So the test value, z equals 2.04. So we've done that, right? You would have to do this calculation in this approach as well. Compute the test value. Did it. This is another approach to doing the same problem. Okay. Next, find the p-value. So here's what we're thinking, right? So here's my mean. That's 0. Z equals 0. Here's 1. Here's 2. So 2.04. Here's 2.04. Right? So I want to determine this probability here, this area here, this p-value. That p-value stands for probability value. So I want to determine that probability, that p-value right here, that p-value associated with z equals 2.04. And I do that by going to the z distribution table. The same kind of way I thought about here, where this is symmetric, so negative 2.04 will give me to the left, the area to the left. And that's symmetric, so it'll be equivalent to the area to the right of 2.04. So if I look to the left of negative 2.04, I'll be good to go. So 2.04, oh, negative 2.04, sorry. I could have done it that way too, but I would have to subtract from 1. So negative 2.04 is 0.0207. 0.0207. That's my p-value. We're going to do this process again for number 15. 0.0207. Is that what I said? See, I talk so much I can't even remember. Negative 2.04. 0.0207. Yes. Okay, perfect. So this is our p-value. Here's our p-value. Important value here, p-value. Here's our p-value. So now the deliberation. So, okay. So we've gotten our p-value, find the p-value. And now we're ready to make our decision. Decision is if p-value is less than or equal to alpha, reject the null hypothesis. If p is greater than alpha, do not reject the null hypothesis. That's the analysis. So I'm checking 0.0207 against my alpha value, which is 0.01, which is larger. 2 is larger than 1. So my p-value is greater than my alpha, so do not reject the null hypothesis. And that's the p-value method. We get the same conclusion using either approach. So you can feel free to use either approach that you favor, especially when it comes to these z-tests. I'm going to do the same process again with number 15. I'm going to show both approaches and we'll see. And again, whichever you like, you like. Okay. 15. All right. A test is made of H sub 0. Null hypothesis is the mean, population mean equals 66. In our book, the null hypothesis is always a statement of equality. It's always the mean equals something. The alternative hypothesis has 3 different possibilities. In this case, different from 66, not equal to 66. The alternative hypothesis can also say the mean is less than 66 or the mean is greater than 66. Those are our 3 possibilities. That's it. That's it. Null is always equal to. Alternative is less than, greater than, or not equal to. Those are your 3 possibilities. In this case, since not equal to, this will be a two-tailed test. Two-tailed test. It can be different from 66 to the left, less than, or different from 66 to the right, greater than. It can be significantly different to the left, less than, or it can be significantly different to the right. Yes? And alpha is 0.01. So this is symmetric. We have to split that. So 0.005 in each of these regions. 0.005. It's like our Z alpha over 2 when we're talking about confidence intervals. It's like that kind of situation. Okay, so N is 80. Number of values is 80. X bar, 74. Population standard deviation is 29. So this is a Z-test. We know the population standard deviation, and N is greater than or equal to 30. And we already have the alpha level is 0.001. Okay. So again, the first method, the traditional method as it's called in your book. So we've got the traditional method, and we'll also do the p-value. Either or, you choose which one you like. So we've got the first step of each method down. State the hypotheses, identify the claim. So the second step in the traditional method, find the critical values from the appropriate table. So the critical values, again, are based on this alpha level of 0.01. I showed here, since this is two-tailed, not equal to, right? Two-tailed, split that alpha in half. 0.005 in each region. So once I look at the table and I get the area to the left as 0.005, which is what? You might remember it, you might not. 0.005 is right here, right? 2.58, negative 2.58. So here, negative 2.58. Here, positive 2.58. Okay, that's the second step. Find the critical value. That's our critical value. So that's our rejection region, right? So when we calculate the Z test statistic, if that test statistic falls in either of these two regions, that would mean that our population mean is actually different from 66. It could be less than, could be greater than. In either case, it's different if it falls into either of these regions. If it doesn't, then it's not statistically significantly different. Okay. So we've got our critical value, right? Values in this case. Now let's compute the test value again using this formula back here. Doing a z-test using the z-test formula. Okay, so I'm going to write that formula down. Okay, let me use a different color. Let me use green this time. Green for go. Z equals x bar minus the population mean over sigma divided by the square root of n. We have all that info there. X bar is 74 minus 66 divided by 29 over the square root of 80. Again, I'll do this piece by piece. 74 minus 66, I think that's 8, right? That should be 8. I do not know the square root of 29. No, I don't know 29 divided by the square root of 80. 3.2423. 3.2423. So Z is going to be 8 divided by 3.2423. 8 divided by 3.2423. 2.467. 2.47. It's pretty close. Okay, so now I look to see. So, okay, yes, we've computed the test value. Now we make the decision to reject or not reject. Where am I doing? There we go. Is this value in either of these critical regions? 2.47 is somewhere out here. Nope, it's not. So since it's not in the critical region, do not reject HO, the null hypothesis. Don't reject it. Don't reject it. Don't reject it. Don't reject it. P-value method. All right, we know the steps. First step, get the null and alternative hypotheses down there. Identify the claim if you can. Compute the test value. We've done that already. Test value Z equals 2.47. And I forgot to use a new color. Let's use purple. Z equals 2. I need to erase this. And don't judge me, please. Okay. So Z equals 2.47. It's our test value. So, excuse me. So we're looking for Z is 2.47. Again, we're looking for, let me see, let me draw this out. So here's 2.47. Remember, this is two-tailed, right? This is two-tailed because the mean is not equal to. This is two-tailed. So I need this area or this area. Either or I can find, right? So if I find less than negative 2.47, that's what the table gives me. Or if I look at 2.47, I've got to subtract that from 1. Either or. Just look at the table for 2.47 or look at the table for positive 2.47 and subtract from 1. I don't like the extra work, so I'll just look for negative 2.47. Negative 2.47. Negative 2.47. That looks like 0.0068, right? 0.0068. 0.0068. So this area is 0.0068. But this is two-tailed. This area is also 0.0068. So my p-value is really 2 times 0.0068. Right? Because each of these areas is 0.0068. So my p-value has to be 2 times that. I hope that makes sense. So my p equals 0.0136. That's my p-value that I'm comparing with alpha. Okay? When you have a two-tailed distribution, a two-tailed test, you have to multiply that area defined by 2 because you've got those 2 regions with that same area. So let's compare 0.0136 to my alpha level of 0.01. Aha, my p-value is greater again. Do not reject the null hypothesis. That's the key here, right? Because if you just use 0.0068, you would have said the other way. You would have said the alpha value is greater and you would have rejected the null hypothesis. It's important to make sure that you multiply that by 2 if you're using the p-value method for a two-tailed test.